Good afternoon, everyone. So last week we discussed about the serviceability limit state. So how to design or check the serviceability conditions, especially deflection and crackings. So we will continue from there. Other give me a second. Where it is. Okay, so we'll discuss about how to do the ultimate limit states. So in the deflection and the crackings, generally we look at how to check. So we had deemed to comply method and the simplified method. So that once you have that deflection, then you can proceed with the bending moment and shear force checks. Then you can go to the cracks as well. So it's the order can be different if you want, but it's always better you start with the deemed to comply deflection standard to check your assumed depth is correct or not. Because if the depth is not good enough, you need to redo everything again. Okay, so that's a problem. So if you have, or if you ask to design a structure, okay, you don't know the thickness or the depth of the member, to get the depth load, you need to have thickness or dimensions. So when you assume something, you need to make sure the assumption is reasonably okay. For that, you should be able to use deemed to comply method for the deflection. So in these some textbooks, they give some approximate or thumb rule at the end of these textbooks, so that reference textbook should have some guide to assume some thickness. So that is basically that come from the deflection deemed to comply deflection check. So if you know how to do the deemed to comply deflection check, they should be fine. So you assume and check it. If not, increase the depth. So today we will see how to design the reinforcements. Then we will go from there. The first question is the question and solutions are there, but those who don't have, so you have what's happening here. Okay, so if you look at that first question, a singly reinforced beam with a cross-sectional dimension is given. So the depth and the width is given here. Okay, so and he asks you find out the mu value for the beam if you use 4 in 20 bars, and if the M star is 150, what is the EST value? So there's both way you should be able to do it. So if you have such a question, so first we will do it the rectangular section, then we will look at some complicated cases. So if you have something like that, so here this is B, the overall depth, and you have this is small d. Okay, so if you ask to do something to find out the reinforcement for bending, so you should use this one. So in ultimate case, the neutral axis will be here. Neutral axis is the axis where the strain is 0. So the strain distribution this is the concrete strain, this is the steel strain. We assume there is no concrete below the neutral axis because concrete cannot take any tensile strength. We assume that in the ultimate case, in ultimate limit state, we assume tensile strength is equal to 0. Okay, tensile strength of the concrete tensile strength is equal to 0, so there is nothing below the neutral axis because here the compression, here tension, so neutral axis stress is equal to 0. So then we use the approximate rectangle because we use approximate rectangle, so this is alpha to f dash c and this is gamma dn. Dn is the depth of the neutral axis. So if you have a uniform stress distribution, you will have a force, and here in steel you'll have a force as well. There is no concrete below the neutral axis, so there is no force from the concrete below the neutral axis, so only steel force. Okay, there is no force. So this is common for both cases. If you have moment, or for question 1, part 1 and part 2, the same diagram will be used. Okay, so part 1, here they gave AST is given. So area of steel is given, so this is area of steel. So here they give as a 4 in 20 bars. Okay, 4 in 20 bars. So the AST is given. Okay, you should be able to use the AST. AST is given. So 1 bar is a pi r squared. Yeah. So in 20 bars, normally there is a chart. So if you want, you can. It's a 314. So AST is a 314 times 4 roughly. you'll get 1252. So you have AST. If you have AST, the question is easier. Okay, if you have AST, the question is easier because you should be able to find out FST. So FST is equal to AST times FSY. The steel is assumed is a fully yielded, so you should be able to get 1252 times 500, this much of Newton. Okay, this much of Newton. So if you work out 626 kilonewton force. So the steel will have this much of force, So I need to find out, because the gamma dn is unknown. If you want to find out the moment, this is a z. Yep. So you need z is equal to, from here to there, that is small d. So d minus, from here to there, small d. This is gamma dn. So this is rectangular stress. So it's a half, will be half gamma dn by 2. So if you want to find out the moment, you need the z. D is given, gamma can be found, there is an equation in the standard. So I need to find out dn, then only I can find out the moment. So to find out dn, Fc, we have two forces, both should be equal. Fc is equal to Fst. So Fc, stress, uniform stress times area. So if you bring that one here, so this much of area have uniform stress. So V times gamma dn is equal to Fst. Okay, so you need to have the alpha 2 and gamma from the clause 813. So they said alpha 2 is equal to 0.85 minus, you don't need to memorize, the standards are given. So you should be able to, F dash C is the strength of the concrete, you know that one. So if you substitute, you will get 0.802. Just make sure it is more than 0.67. Cannot go below that value. Gamma is given by this equation. Everything is given in this clause. F dash C is the concrete strength. That is given as 32 MPa. Okay, so if you substitute 32, you will get 89. That also should be greater than 0.67. So we have these two. So we know this value, you know this value, 32. B is given 250 gamma. So this one is known. So if you substitute the dn, if you substitute everything, you get dn as 110 millimeter. Okay, you substitute everything, you get 110 millimeter. So this is the depth of the neutral axis. We need to do one check, okay, because all these workings are based on a couple of assumptions, the steel yielded and everything. So we need to make sure it's within the required things. So I need to find out Ku first. Ku dn upon d 110 divided by d is given, isn't it? 350. So you will get 0.31. So that is less than 0.36. So if it is less than 0.36, the ductility requirement has satisfied. Okay. So if it is less than 0.36, it's also under reinforced section. If it is under reinforced section, steel will yield. Sorry, so steel will yield before concrete reaches the 0.003. So that's assumptions are correct. Okay, so it's satisfied. So I can proceed. So Z value, this one, D minus gamma dn by 2. You know that gamma, you know the dn now. You should be able to substitute. That value. So 110 minus, 350 minus 0.89 times 110 divided by 2. So you will get the Z value. So the mu is equal to FST times Z. If you have two equal forces acting parallel, you have a moment is equal to force times the lever arm, Z. So if you substitute, FST is known, Z is known, so you will get 189 kilonewton meter. Please work out, the units are important. Okay, take pen and paper and work out, then only you will understand what's the problem. Okay, units should be correct, and if you have any problems, let me know. If you read this one, it looks easier. Okay, because everything is substituted, so you should be able to understand. But if you take pen and paper and see whether you should be able to get same answer. The part 2 is little bit complicated compared to part 1, because it's not mu. Okay, so here they gave M star mu. M star has 150 kilonewton meter. So they said M star is 150 kilonewton meter. So they asked, what is the EST? Earlier EST is given and you asked to find out moment. Here moment is given, you need to find out EST. So this part you need to go backward, but little bit complex, because EST is unknown, dn also unknown. Okay, when you work out from here to there, EST is known, only unknown is dn. All others are known in this diagram. But when you work out from the backward, little bit extra maths, but method is same. So the standard says M star should be less than or equal to pi mu. Yeah. So this is the ultimate limit state criteria. So 150 pi for the bending moment.
Pi 0.85.
0.85, yeah. So this is 0.85 mu. So where that comes from? Table 2 point, isn't it? 2.22.
3 point is 4.
That is for steel, I think, by mistake, I think we need to change it. 3.4?
Yeah. 3.4.
Okay. Okay. Double check because it's a 2 standard I'm teaching. Sometimes I'm teaching the steel as well in the undergraduate. Give me a second. Give me 1 minute. Oh, sorry. This is 2.22. Right. If I mentioned that one yesterday, this is the standard 2.22. For bending without any axial, this one, okay, this is the KU, so this is the pi value. If you substitute any K value less than 0.36, you will get 0.85, okay, because it can't exceed 0.85. So your KU value in this case is a 0.31, yeah. So if you substitute the KU in that equation as a 0.31, 1.24 minus 13 times 0.31 divided by 12, you will get a number larger than 0.85. So in that case, the pi is equal to 0.85. Okay, so it cannot exceed 0.85 and also it cannot go below 0.65. It should be within that one. But if you use anything, any K value that is equal to 0.36 or less, then you will get 0.85 as an answer. So from here you should be able to get the mu value. Mu should be 150 divided by 0.85, so 176.5 kilonewton meter. So technically you need more than 176 kilonewton meter mu. So when you use this steel, you get 189. So probably our steel will be little bit less. It's almost very same order, yeah. So it will be little bit less, but at the moment we don't know, so we need to work out. So if you want to get the mu things, so go back to this, the diagram. Here AST is unknown, so FST is equal to AST FSY, but I don't know the AST, so I can't calculate. Earlier I know this one, so I should be able to calculate, but I don't know that. FC alpha 2 F dash C gamma dn times B. So the same equation for FST and FC. Okay, doesn't change, same things, but only thing is earlier only dn is unknown, AST is known, but here AST and dn are unknown, so two unknowns. Okay, so what we need to do, we need to find out AST and dn, two unknowns. Earlier dn is only unknown because AST is given. So I need to write some equations. So the first one is equilibrium equation, that is what I write earlier. So I will write that one. Fc is equal to Fst. So alpha 2 F dash C gamma dn times B AST Fsy. That is the first inequality. The second one, first equation. So the second one also I write here. Mu is equal to Fst times Z. So AST Fsy. Z is equal to D minus gamma dn by 2. Same things, nothing changed. Okay. So I have two equations. I need to solve them. So technically what we'll do is, you need to either substitute AST Fsy, this one here, and you'll get an equation. Mu is known, Mu is 176, Mu is known, it should be larger than that. So you need to, otherwise gamma dn can be substituted here. So either way should be okay. So I will Mu AST Fsy D minus gamma dn. Gamma dn is this one. So this one is equal to this divided by these three. So I'll put AST Fsy divided by alpha 2 F dash C times B, there's a 2. Okay. So I substitute gamma dn from this one here. So in this one, Mu is known. Mu is equal to how much? 176. So this is 176.5 kilonewton meter. EST unknown. This is 500 MPa. This is 350 millimeter. MPa. So this is unknown. Here also unknown. Alpha 2 we already calculated. Alpha 2 is 0.802. This is 32. This one is 250, isn't it? So if you substitute, what you will expect? You will get a second order equation. Yeah? Second order equation. You should be able to calculate AST. Do you know how to do that one? So and I think in the study guide I put the final solution, isn't it? The study guide. But how to do it? Do you know how to use the Excel to solve this one? How many of you know how to use the Excel to solve these kind of things? You know, second order equation, you will get something like ax squared plus bx plus c. You will get this form, and you should be able to get x, isn't it? X equal to minus b plus or minus. You know that one? This is second order equation, AST square. Yeah. Do you know how to get this one? How many of you know? How many of you know how to get the AST from this? Substitute all these values. All the values are known. Can you get the AST?
Yes, sir.
Okay. Anyone have any issues? How many of you know how to use Excel to solve it?
Sir, I don't know about the Excel, but I can use the calculator to solve it, sir.
Oh yeah, graphical calculator will give that answer, isn't it?
Yeah.
Yeah. So if you don't have a graphical calculator, what you can do? I don't have a graphical calculator. So just put the things here. FSY. FSY is how much? 500. It's a unit is MPa. Okay. So what other things? Fix that one. It should be MPa, capital. Okay.
Sir, we got MU.
Wait, I'll come to MU, but small d.
Small d, 350.
350 or 250?
350.
Huh? Wait, sorry, I might put it wrong number there. What is the question says? 250 or 350?
Questions.
250, isn't it? Sorry. 250.
So B is 250, sir. Question is using the B is 250 and
no,
D.
D is 350. Says correct. Sorry, yeah. Okay. So B is 350. Sorry, D is 350. And what else we have? EST is over there. FSY there. Alpha.
2.
Alpha 2. What is the value?
0.802. Yeah.
And
And
F dash C, isn't it?
FST, yes, sir. FST, yeah.
FSC already have.
32, sir.
Huh?
We got B equal to 250, sir.
250, yeah. Okay. So I don't know the AST. I just put some numbers. Okay, I don't know that one because I did for the Excel. You need to give the number, which I don't know at the moment. Let's. Okay. So if you have this one, I will put MU equal to. So what is MU is equal to AST? Huh?
Yeah. Yes, sir. AST into FY.
FSY.
Yes, sir.
And bracket. Oh, sorry. We need to put a bracket. D.
So D. Yeah.
Minus. Yeah. I put a bracket again. AST FSY. So AST FSY divide by 2 times alpha 2 times
FT
dash C
into
times B. So this much of what is a unit?
Yeah, it's Newton, sir.
Newton millimeter.
Millimeter, yeah. We need to divide by 10 to the power 6.
Yeah, so that is equal to this one divide by
10 to the power 6.
10 to the power plus 6. So you get kilonewton meter. Yeah. Okay. So this is normal things, but I need this one. Okay.
Yeah.
So there is a function. You can change the number and get it 176. But what you can do is there is a function. Data. Go to the data. Okay. Go to the data. It is I think it's a useful tool to solve some complex equations, second order, third order, whatever. So what if analysis, goal C. So you have something like that. Okay, under the data, what if analysis, goal C. So set this cell. So you select this cell. Okay. To what is the value you want? 176.5.
Yeah.
By changing
Yeah.
this one,
Yes. Okay.
so it will do all this calculation for you, and it will give the AST as 1156 or 157. Okay. So it's 1 minute, and you can do as you like. Okay. So the goal C will give, otherwise your calculator, whatever. So you should be able to find out the AST as 1156 or 57.6. Okay. So in the study guide, if you go through the study guide, I'm not sure, I gave this solution. So solving this to the second order equation, you will get, you know, the minus b plus or minus b squared plus 4ac, something like that. You will get that form. So you can substitute into that one, you can also get the solution. But I think in the exam or wherever, it is much easier if you go from the first principle and get this one and solve using your calculator or using Excel. So now we have the 1157 or 58 millimeter square. So I need this much of steel. Okay, but there is one more thing I need to make sure, because there is a minimum steel requirement. AST minimum. What does that mean is, so the standard says sometimes if you have very small moment, you require only small area of steel. But the steel says, so the standard says, whatever the area, you should provide at least this much of steel. So that is called minimum steel. So that is given. Okay, you should be able to get that minimum steel area in the standard. If you go to the section 8, so here this is the alpha to gamma values I talk about. Yeah. So the minimum strength requirement or minimum area requirements I explain in the next page. Say 816 minimum strength requirement. So whatever the bending moment you have in your section, they said at least your section should have this much of moment capacity, minimum. Okay, so this is the minimum capacity, but you don't need to check that one. So you just need to provide this much of steel, is automatically give this much of moment. So they said your AST should be larger than this value. So for rectangular section, the alpha value is given by this equation 0.2. So here we have rectangular section, so it should be 0.2. D and small d is unknown. This is FCTF. Where to get that value? That is a fractional strength of the concrete. Where to get that value? What is FSY? Steel yielding strength, that is 500, yeah, in tight bars. So what is the fractional strength of the concrete? The characteristic strength or compressive strength is given as a 32. So what is a fractional strength? You should go to, if you are not sure about the material properties, if you are not sure about the material properties, you have to go. Yeah, you need to go if you don't know the material properties. Section 3. Okay, section 3.1 will tell you the properties of concrete. So if you go to that, so if you go here, you can see the fractional strength of the concrete is given there. Fractional strength of the concrete is given by 0.6 times square root of F dash C. Okay, you should be able to get from here. So you go back to the section 8. So minimum area, AST, whatever you provide should be larger than this one. This is the minimum area. So if you substitute all the values, so I will write here. So that is given by alpha B d upon d squared F dash CTF FSY times BWD. So if you substitute that one, 0.2 for rectangular section is a 0.2, capital D is a 450, I think. Is that correct? 450. Yeah, sorry, 400. So that is 400. Small d is given as a 350. So this is 0.6 square root of F dash E, 32 MPa, 500. B is 250. D is 350. Okay. So if you substitute, they said you will get 512. If you substitute, you will get, sorry, my apology, 155.2. Let me just get. So that, what does that means? They said you should provide at least this much of steel. Okay, but your steel is more than that, so that should be okay. So the AST satisfied. And we also need to calculate the DN. So if you know the AST, you should be able to substitute here and get the dn. So you also can get from the dn is equal to 10136 millimeter. So I need to check the Ku value. That also fine. So answer is AST is equal to 1158 or 57.6. Okay. So the finding AST is not finished. So finish the question. So you need to check the minimum values and the limits. Okay. So this is how normally we do with the normal singly reinforced sections. Okay. So you should know if the AST is given, how to do the MU calculation. If MU is given, how to find out AST. Any questions? So the next question, is about the doubly reinforced section. Okay, so we touched a little bit, but we haven't gone into the detail. We will look at that one now. So when you have the singly reinforced section, give me 1 minute. When you have one singly reinforced section here, you can see that earlier, the first case, the AST is at 1252, and we end up with 189. Yeah, 189 MU. So then the AST is 1158, little bit less. So the MU also little bit less, 176. You know. So what does that mean? If we need more moment, we need more steel. Yeah? You increase the steel, what will happen? When you increase the steel, what will happen? You increase the steel, the MU will increase. Yeah? MU will increase. Do you think that is a case forever? Do you think that is a case forever? That means, can you increase? So here, so you have the steel, yeah? So this is Dn. So this is D, this is B. So we know the AST value. You increase the AST, what will happen? MU will increase. Yeah? Is that correct?
Yeah.
That's what we look at now. We have two cases. One is AST is 1158. For that, MU is equal to 176 or something. But in the part 1, when you use a 1252 AST, the mu is a little bit higher. So if you need more moment, or if you have larger moment, we need more steel. Okay, more steel. So what actually happening here? Zero 0.03, we cannot change it. Yeah,
Yeah.
we cannot change. So this is the maximum. So if we increase the moment, the dn technically will increase. dn will increase. So that means for smaller moment, it will be like this,
Okay.
and it will comes like this. No? So as we increase the moments, it will go like this. So the dn will increase. Earlier with the smaller moment, dn is here, then it will increase like this. So as you increase the moment, actually when you increase the moment, dn will increase. Okay, or AST, when you increase the AST, dn will increase, and that will increase the moment. When you increase the dn, what will happen? So here the Fc value, this is Fst. Yeah. So when you increase the dn, gamma dn will also increase. Yeah. Fc will increase because alpha 2 F dash C gamma dn times B. So when you increase the dn, this will increase. Yeah?
Yeah.
So Fc will increase. So Fst will increase because this and this are equal.
Different.
Yeah? This and this are equal. So this will increase. So technically you will have larger moment. So you understand this one clearly. You increase the steel or you increase the moment, whatever. Okay. So you increase the steel, so that will increase the dn. So that will increase the Fc. Yeah. So that will also increase the moment. Another way, you increase the moment, it will increase the dn. To balance, you need to increase the AST, and it will give the larger moment. So larger moment means larger steel. But what is the problem here? When you increase the steel or moment, dn will increase. Yeah, dn will increase. What is the maximum dn we can go? 0.36. Okay, because Ku value for ductility. So dn should be less than this one. If we exceed, the ductility requirement will not satisfy. But where they said you cannot exceed, do you have any standard says you cannot exceed? Do you have any standard says you cannot exceed 0.36? No, nowhere in the standard they mention that one. But what they do, they put this limit in a little bit different ways. So if you look at this pi value, here. Okay, if you look at this one, so here up to pi 36, if you substitute any Ku value, sorry, up to Ku is equal to 0.36. If you have calculator, you can check it. Any value you can put 0.36 or less. Okay, you will get pi is equal to 0.85. If you substitute K is equal to 0.36 there, you will get exactly 0.85 as a pi value, because pi is equal to 1.24 minus 13k. Okay, so if you substitute k you as a 0.36 or anything less than that, you will get a value larger than 0.85 or equal to 0.85. So then it will limit, because it cannot exceed 0.85. So the maximum is, okay. So up to this one, no problem. But if you go more than that, .545, okay, so up to this value, pi is this one, okay. If Ku change or increase beyond 0.36, the pi value change from 85 reduce to 0.65, start to reduce. Okay, so this is the ductility limit. What is this limit? Under reinforced, over reinforced limit. Okay, so we cannot go beyond that one, because in that case the steel may not yield. So the Ku value increases beyond 0.36, pi value will reduce. So the M star Mu will increase if you exceed the 0.36. If you exceed the 0.36, Mu will increase. Okay, you increase the AST, so Dn will increase, so you get a better Mu. So Mu will increase, but pi will reduce. Okay, if you exceed 0.36, still you will get large Mu, but pi will reduce. So the multiplication may not change much. So if you put additional steel, Mu might be larger, but your M star will not change much. Okay, so there is no point of putting too much steel beyond 0.36 Ku value. Okay, so in that case, what we can do, if you still need more moment but we reach 0.36, what we can do, we'll use the doubly reinforced section. So what we do is, so we reach a limit for AST. Okay, so let's say this is, when you put this one, Ku is equal to 0.36, you already reached. So yours, the neutral axis is there, so you have the strain distribution. So you got 0.36 with this AST, I don't know how much, but for this AST you reach 0.36. So that is the maximum AST you can provide at the moment, because if you provide anything more, what will happen? KU will increase. If you put anything more, than this AST for the KU is equal to 0.36. If you provide any additional AST, the DN will increase. So that means KU will increase. Yeah. So KU increase means the pi will reduce, so there's no point of putting additional steel. But I still need more moment. Okay, still moment capacity is not enough. I need larger capacity. So what I can do, because at this stage I cannot move DN further. Okay, so what I'll do is I will provide some additional steel. I'll put some additional steel. Okay, but to balance that one, I will also put some steel here. So this red color will balance the forces. Okay, so this will give some force, and the red color also will give force. This force and this force, not area, this force and this force will be balanced. So if you have balanced force, the neutral axis will not change. So the DN doesn't change, so the KU is still 0.36, but I put additional steel here and there, so I can get higher moment capacity. Okay, so this is called doubly reinforced section. So doubly reinforced section means you have some reinforcements in compression zone. The reason is to balance the extra steel we provide here. Is it clear? So in this case, the DN still within the 0.36 or less, cannot exceed. But this one, this is called compression reinforcement, ASC. So we have some additional reinforcement, ASD dash. So this ASD dash and this ASC, C for compression, T for tension. Okay, so this compression reinforcement, this tensile reinforcement gives same force. Okay, whatever the force given by the compression reinforcement should be balanced by this one, so the DN doesn't change. So remember, it is not necessary this compression reinforcement will yield. Okay, that is important. It is not necessary compression reinforcement will yield. Okay, tensile reinforcement always yielding. Okay, but compression reinforcement is not necessary, because we put the compression reinforcement just to balance the extra force, given by this additional steel. Okay, so that is the basic principle of doubly reinforced things. So if you cannot manage with a simply reinforced section, so you should be able to use doubly reinforced sections. Okay, so that's when you have very large moments. So if you look at the question 2, they said a rectangular beam, cross-sectional dimensions are given, a compressive steel of 2 to 6 and tensile reinforcement of 6 to 8. D is given, ds is given, calculate the design moment capacity. So in this case, what we need to do, so there is no change in the calculation or method of calculation. If you understand one, it is easier to work out the rest of the things. So this is the neutral axis. We don't know the neutral axis, but this is the neutral axis. The strain distribution. So this is 0.003. So we have reinforcements, main reinforcement, that is here. And we have also some compression reinforcement, that is given as a DSC. So this one I put steel area is, so this include the additional steel, okay, and this is the compression reinforcement. So we have something like this. So if you have, this is the DN, don't worry about the compression reinforcement, it will sitting as it is. So you just first think without compression reinforcement. If you don't have compression reinforcement, you have a rectangular stress block and you have FC, sorry, FC, alpha 2 F dash C, gamma DN, yeah, and you have a steel FST. We have an additional term here. There is some force will be there. This is FSC, that is an extra term because of the compression reinforcement. Okay, all others are same. So I don't know the dn value. I don't know the dn value at the moment. So I will write the equation for each and everything. First, we'll go from here. FST, force in the steel. This steel will yield. Yeah, tensile steel will yield. So AST, area times stress, that is FS1. Okay. The next one is FC, uniform. This one alpha 2 F dash C, that is a stress, times B times gamma DN, that is same as earlier one, doesn't change. Okay. So the next one is FSC. This is the new term. ASC, area time stress. Stress in the compression reinforcement. Fs, not Y. I don't know whether that is yielding or not. So I will put as a Fs. Okay. Yeah. Important. I put Fs. It can be Fs5. I don't know. Okay. If it is reached the yielding point, that is Fs5. But at the moment,
Sir,
I don't know. Yes.
Excuse me, sir.
Yep.
Sir, it's necessary to reach the every reinforcement to the yielding point?
Hmm?
Is this necessary to reach every reinforcement provided on to reach the yield point?
Every necessary to check.
No, sir, we can check that, but sir, you said that Fs and Fsy, there is a difference between Fs and Fsy. But we can use the same value like N20 or N10 bar, same value for the both.
Yeah, so this is the yielding strength.
500.
If it is reached the yielding point, it will get the yielding stress. But if it is not reached the yielding point, then so it is like that. Steel So this is Fsy. This is stress strain. So if you strain into your steel, this is the steel. So if the steel strain is reached the yielding point, after that the stress will not increase. So if it is somewhere here, if this one is then stress is equal to Fsy. But if for this one we don't know whether that is here or here. So if the strain is here, then stress will be a little bit less. If the strain is here, then stress is Fsy. Is it clear? Or not?
Yes, sir, it's clear.
So this is the stress strain relationship. I'll put it a little bit larger if you want. So this is the stress strain relationship we use in the concrete design for steel. Okay, so steel material property is assumed like this. That is what yesterday we discussed. So this is the yielding strain and this is the yielding stress. So if the steel strain reach the yielding point or beyond that, then the stress is equal to Fsy. If the strain is somewhere here, then stress will be this one. Okay, so we need to know the strain. This strain, this is the tensile reinforcement, the strain in the concrete, this one. This is the strain distribution. This is the strain distribution. So we need to know what is the compression reinforcement strain first. Okay, you don't know the strain, so we need to find out. So how to find out this strain? So this is the normally that is an assumption. This should be reach the yielding point, otherwise it's not satisfy the Australian standard. So this should be satisfied. So the tensile strain will be somewhere here. If you calculate, you can calculate. So the yielding strain, this is 0.0025. Okay, so if you calculate the strain here, it will be definitely more than 0.0025, but this one sometimes it may reach the yielding point, sometimes no. So we need to calculate. To calculate that one, we use the similar triangle. So this one divided by that equal to this one divided by this. Okay, similar triangle, 0.003 divided by dn equal to this one, I don't know at the moment, by here. Okay, divide by that. So this is dn, this is dsc, so dn minus dsc. Okay, so at the moment I don't know this value, I don't know this value, both. dsc is given as 40. Okay, so if strain is less than yielding strain, Fs equal to the stress in the material will follow the Hooke's law. This is the Hooke's law line. So steel Young's modulus time the strain. If it is larger than or equal to yielding things, Fsy, so if it is somewhere here or anything after that the stress will not change, that is equal to, sorry, Fs equal to Fsy. So at the moment I don't know the dn, so I can't definitely say whether that is yielded or not. So generally we will go with this one. So most of the compression reinforcement will not reach the yielding point most of the time. Okay, so based on that, this is the most of the cases like this. So Fsc times if you put it here 0.003 So now this is the only extra term in the doubly reinforced section. Okay. So now for the equilibrium equation, this plus this equal to that. Okay. So this and this compression, this is tension, so it should be balanced. So Fst equal to Fc plus Fsc. So what is this one? This is AST Fsy alpha 2 F dash C gamma dn times B plus ASC ES okay. Is it clear? So what is AST? They gave this AST as 628 millimeter square. This is 500. And what is this value? Gamma, so alpha 2 we already calculated for 32 MPa. There is an equation. Okay. .802 32 MPa this also we calculated in the previous one, so you can use the same number because that same F dash C. dn I don't know at the moment, dn is unknown. B is given as a 200. ASC is given 226. dn is unknown. D is given as 360. DAC is given as a 40. So what is the ES? 200 gigapascal. So we need to make it as a mega. Everything is a mega. So 10 to the power 3. Okay. So everything is known other than dn. So you can use your Excel or Gold-Seek function or your graphical calculator, you should be able to find out dn. Okay, so if you calculate the dn, you will get 59.1 millimeter. So it's not finished yet, because all this one is based on this assumption. So I need to calculate the strain, because I need to calculate the strain. So strain is equal to 0.003 upon dn minus dsc. So now you know the dn value, so you should be able to calculate. So if you calculate 0.00097, so this is less than 0.025, so that is 0.0025. so it's 3 zeros, so it is less. So our assumption is correct, so all the calculations are correct, so dn is correct. So if you know the dn, so because if this one is not correct, you need to assume other way. It is greater, so you need to put it fsy here and recalculate the dn value. Most of the cases, compression reinforcement will not yield, so this will be the case. So then Ku value, all other checks, dn upon d, 59.1 upon 360, you will get 0.16. It is much smaller. Okay, and mu value. So I need to calculate mu value. So earlier we have only two forces. So when you look at this one, so when you look at this one, so you have only two forces, so the moment is equal to force times distance, because if you take the moment about this point, this times this distance, so if we take this one moment about this point, fst times z, so that's easy. So now we have little bit different. So the easy way is take the moment about this point. So here fsc times this distance plus fst times this distance. So mu fc, the distance from here to there is a d, small d. This is half gamma dn. Okay, so it doesn't change, same d minus gamma dn by 2. So this is if you have only one force, also same. Okay, but here fsc, we have another additional term. So the distance from here, so this is d, this is dsc here. So d minus dsc. So you know ft value, you know fsc value, because now you have the dn, you should be able to calculate. Okay, so you should be able to get the mu value. So this is how we calculate that. This is how we calculate the moment capacity for doubly reinforced section. Any questions? Do you have any questions or we haven't done the shear, isn't it, yesterday? No, we haven't discussed. Okay, do you have any other questions? The next question is the shear. We'll work out next week. But do you have any other question? Otherwise, I need to little bit talk something extra from here. Anyone have any questions so far?
No, sir. Good to go.
Okay. So now we work out everything with a rectangular section. Yeah. Everything we discussed so far is about the rectangular section. So in the normal construction, slab and beams are constructed together. Okay. So we don't construct beam and then we put separate slab. It's not the case. It is true in the case of precast members, but in reinforced concrete, normally the beam and slabs are casted together. The formwork, if you remember or if you see any construction work, the beams and slabs are constructed together. So if you look at that, the slab beam construction, so it looks like this. Okay. The beam and concrete slabs are constructed together. So technically we call this as a beam, yeah? Isn't it? Technically this is beam
Yes.
and this is slab. So this part is common.
Yes.
Okay. So when you have the bending, when the slab, so when you look at this, just put as a line. So when the slab bends, it will not bend like this. So it will bend, generally take like this. Okay. So some of this part will try to give bending moment in the beam as well. Yeah. So because this casted together, we can separate the slab and beam something like this or something like this. Okay. So in this case, in the design, we need to consider this section as the beam. So a little bit on the slab should be included. So generally the end beams are L-shaped. Yeah. And the middle beams are T-shaped. Okay. L-shaped. And
we are all one here.
any questions? So
Yeah, then make sure we get that back up for everyone involved. care about your fellow students around here, but also just to treat them as human beings. Respect to their culture, their language, and their ethnicity and gender.
Sorry, if you don't, could you please mute your phone if you don't use.
But and as you people keep each other's space and then say, use the right pronouns, which is something I need to learn also.
Hello? Can you mute your phone? So all are recording. Sajid? Sajid? I'm not sure. Could you please mute your phone because everything is recording. Okay. So in this case, it become T beam or L beam. Okay. So in this case, the design is slightly different, not too much. So the T or L beam looks like this. So you have the reinforcement here, yeah? So same things will happen. So you put the strain distribution. It is 0.003, okay? Then stress distribution. Alpha to F dash C. Okay. So if you look at this one, FC, FST doesn't change. AST, FS5, that's the same. So the FC is the one, it's a little bit tricky. So gamma DN, this is DN. So if you bring that one, if the gamma DN is within this flange thickness, okay, if that one within this one, so this is the area, so this is the B effective, so alpha to F dash C gamma DN times B effective. Okay, if gamma DN is less than thickness of the flange. Okay. If this one is little bit below and it comes, say, can come, this line can come down. So if it is something like that, you need to consider this area. You need to consider that area. So this is not the B effective gamma DN. So you need to consider this T shape. Okay. So the area is slightly different, but all the calculations are same. Okay. All the calculations are same. Only depend on where this line fall, whether it's within the flange or not. You might have some variation in the area of concrete. Okay, area of the concrete is slightly different. So this is the normal case when you have slab and beams casted together. But if the slab and beams are separated, so something like precast beam or precast slab, then whatever rectangular beam should be enough. Okay, is it clear? So this is the beam we need to use in our project. Okay, so we will discuss this one during the drop-in session when you work out. So that's what we have a project. So you should remember that depend on gamma dn location, the area of steel might be different. So area of concrete might be different. So we need to be careful when you put that area. It's not always gamma dn times bf. Okay, so it's not always b times gamma dn, because depend on the location of the one, it will change. So we need to work according to that. Any questions? We haven't done the shear. I don't think we have enough time. It will shut down in 5 minutes. So we will discuss it next week. Okay. Any questions? So how many? So we will. How many groups started the project? Huh? Not many. So we'll talk about that one 5 o'clock. Is any issues with the project?